All right, so let's get this. So like I said, I believe we finished talking about um, the melanocytes and how they contribute to skin color. I use the 112 picture of it to kind of show this doesn't do it, justice and how it works. Remember that the melanocytes, the cell body is going to be along the stratum basal, on the bottom. So now we get into looking at the dermis, looking at this middle layer, which is where most of the things that we study are in lab. So again, it's going to have the dermal papilla or papillae, which are the finger-like capillary beds that will cause these projections. It's going to have a lot of different types of tissue we'll look at in a minute. But one of the things we don't look at in lab is the fact that there are two layers to it. It is going to have what's called a papillary layer and a reticular layer. This reticular layer is made up of dense, irregular connective tissue. Not too concerned about you knowing that. Remember, we looked at this in the last chapter. It's not one of the ones we studied in lab, but I said that the difference between dense irregular and dense regular, which dense regular is regularly aligned, densely packed fibers, and they are of tendons and ligaments. This is where there's no arrangement of the fibers. They're going in different directions because this tissue needs to be strong in all directions, if that makes sense. Now, the difference between these two, if I go to the next picture, this right here is that capillary bed we're talking about, the arteries and veins with these little finger-like extensions that go up. If I was going to draw a dividing line between the papillary layer and the reticular layer, it really is that this is about that small. The papillary layer is just basically this big capillary bed that's running underneath the epidermis. Does that make sense? So it's really just a very superficial part to it. Now, we're going to see a little bit of this when we get into burns and stuff and how it relates to it somewhat. But again, the big thing is just understanding the papillary layer is really that capillary underneath there. Now, there's several accessory structures in here. We've looked at hair follicles. We don't look at nails in lab. We barely touch on glands in lab, so those are kind of new things we'll look at. So again, this book, kind of like those membranes we said, it tells you there's 3 membranes and it gives you 4. Seems like they would put the 3 in an organization and then anything added, like indented, so you don't go, wow, that's the weirdest group of 3 I've ever seen, right? But the 3 are, first, the nail plate, all right? The nail plate is the actual nail, right? The nail plate's the actual nail. Underneath the nail plate is something called the nail bed. All it is the skin that the nail plate rests on, right? The nail matrix and I always hate this word, lunula, I always want to throw weird other syllables in there, but the lunula, those are relatively the same. The nail matrix is the actual area where we have the cell growth. Right? It would be equivalent to the stratum basal in the epidermis. This is a little area. These are the cells that are producing new cells. And these cells, unlike the epidermis that go through a process, these pretty much right away turn into keratinized cells. And the lunula, all right, is the little half-moon shaped little white part that you can see that is related to this matrix. So they're kind of one and the same. This is just the part of it that you can see that looks like the little moon peeking out over the back part of your nail. And then the third is this thing called the cuticle. And you don't have to know 1 through 3. I'm just kind of trying to point them out. I don't even know if that's the actual 3, but those are the ones that I would pick. But the cuticle is the epidermis that kind of extends over. It's actually the stratum corneum extends over and covers, usually if you don't have it taken care of, it covers where you don't always see the lanula. So hopefully that makes sense, right? It's pretty basic. These are the two kind of, these three are kind of the main ones. Know the nail plate, the nail bed, know the nail matrix is where the cells are growing. It has a look, and it's this area that we call the lanula, which looks like a moon. That's why it's called the lanula. It's lunar. And then the cuticle, again, is, I think most people know what the cuticle is, even if you have never had a manicure. So far, so good. I always hate pictures of fingers cut in half. It just seems weird, but anyway, so nail plate, nail bed, this little part there's the lanula. The matrix is just deep to it, but this is the part that extends out, and again, the cuticle is covering that back part. Now, the hair follicle we have looked at. One of the things that we don't really dig into, especially in lab, but even in here, we're not going to get too much into it. But I want you to know that the follicle actually is an extension of the epidermal cells. Right? So when we were looking at the hair back in lab, and I told you that if you use the basement membrane as the dividing line, the part of the hair above the basement membrane is called the hair shaft. The part that's below the basement membrane is called the hair root, right? Well, that hair root basically is plunged into, and it almost takes, if you can use your imagination, imagine that this is like this rubber membrane. It pushes in, and then that basement membrane and the epidermal cells will surround it, and that's what makes the hair follicle. Now, in here, all I want you to know is the hair follicle is what surrounds the hair root, right? So the hair root is the part that extends into the dermis, even sometimes into the hypodermis. The hair bulb, again, something we don't look at lab. The hair bulb is, again, this part that's kind of like the matrix in the nail and kind of like the stratum basal in the epidermis. The hair bulb is the area of dividing cells. It is the deepest part of the hair. It's at the very bottom, and that's where we get the hair papilla, the blood vessel that extends to give this nutrients. Right? So the hair bulb is kind of like, again, stratum basal or the matrix of the nail. The hair shaft is the portion of the hair that extends out. It is no longer covered by anything, and it is just dead cells. And then finally, attached to the hair follicle is what we call the erector pili muscle. It causes the hair to stand upright. We call that goosebumps or chill bumps. It causes the hair to stand up erect like a pillar. That's where we get the name for it. All right. Now, also understand hair color is due to melanin as well. So melanin not only is skin color, but it is hair color, and that is why if you have ever seen someone that is an albino, albinism, I think the book calls it, their hair's white, their skin's very white, even the irises of their eyes have no color, and so melanin is the color for the hair as well. Now, we will have sebaceous glands. We looked at these again in lab. Sebaceous glands are going to be associated with the hair follicles. I'm not really sure why it says usually, but as far as I knew, all hair follicles will have it. I could be wrong on that, but anyway, it is associated with hair follicles. It is a holocrine gland. Again, going back to last lecture, we talked about holocrine glands as glands that the whole cell ruptures when it releases their substance. So it is a holocrine type gland. The substance it produces is called sebum, all right, sebaceous sebum. And so sebum is going to be a lot of fatty material in general, obviously cellular debris because the whole cell ruptures, so it's the whole cell. But this is designed to help keep the hair waterproof first and foremost, and it helps keep the skin waterproof. But it also has antibacterial and antiviral and antifungal properties to it. So it's got a lot of stuff that it's trying. And again, the hair root is protected by the follicle. It is just getting ready to go out into the cold, cruel world. So this is its job, is to dump this on it to try and protect it because it no longer is. The follicle is no longer able to protect it. Acne is a result of these glands, right? It's a result of clogging of these glands. And again, it's absence on the palms and the soles, which I hope there's no hair there anyway. So, yeah, all right. So far, so good. Now, sweat glands. I don't remember in lab if we really touched on this or not. I know in some of my labs I did. Uh, but there's two types of sweat glands. Our model only shows one type. It actually is this type. Now, in here again, no pictures. There's going to be description stuff, and so don't worry about it. I'll tell you what the difference is as far as they look. But Ecrine or Miracrine glands, this is the type of gland it is. A lot of times it is referred to as Miracrine, simply because that's the type it is. Remember, a Miracrine gland merely secretes a substance, right? And so Miracrine glands, these are the main type of sweat glands that we would think of. These are the sweat glands that are designed to regulate body temperature. And even though it doesn't say this up here, it's good to know these are active from birth until you die. The fluid that they produce is very watery. There's very little other substances in it. There is going to be some salt and whatever, but it's mainly water. Its job is to get on the surface of the skin and evaporate. Right? So it needs to be mainly water. It doesn't have a very pronounced odor. Right? This is not the kind of sweat that makes you stink. Right? Now, I'm not going to say it makes you smell like roses, but it doesn't make you stink. This one makes you smell like an ape. Right? Apricorn glands. Apricorn gland, again, this is named because this is the type of gland it is. Apricorn glands secrete a part of the cell when it releases its substance, right? Now, these apricorn glands, which are still sweat glands, these are associated with puberty. These become active during puberty. They are going to be found always associated with hair follicles. One of the big differences is on the Miracrine gland, if I got this little gland here, the duct comes up and it goes right to the skin, it causes this to evaporate. If, on the other hand, I have a apricorn gland and I've got my little hair, this duct will go and dump right onto the hair follicle. It's always associated with hair. And the particular area is going to be axillary and groin areas. This is where the hair starts growing during puberty. This is mainly emotional. And again, that's why puberty, people are kind of, the emotions go crazy in puberty, and that's why, it's just always producing this stuff. It is weird to think that really this is supposed to make you smell attractive, but it really makes you stink. I don't know if we've gotten past that or whatever, but again, it makes you smell like an ape. You might not realize this, but if when all of us went through puberty, we stunk. And especially little boys, you could take showers multiple times a day. It just doesn't help. Right? So these are apricorn glands. So these ecrine or miracrine glands are the ones we think of as sweat glands. These are to regulate body temperature. These are what we associate with puberty, and these are going to be more emotionally based. These actually have an aroma. And then oddly enough, there's two weird types of modified sweat glands. Ceruminous, which I think I got that right, because once I say it wrong, it's stuck in my head. This is earwax. These are in your ear. You've got modified sweat glands that produce a very thick, waxy-like substance that's designed to protect your ear. It actually does protect things from trying to get in your ear, and things do. The other one are mammary glands. It's kind of weird to think that that is a type of a sweat gland. And obviously, we know that it produces milk. All right. Those make sense before I go further? Okay. Now, the skin itself, once we look at the skin, again, the cutaneous membrane is absolutely vital for homeostasis. It is the first line of defense. And when you get into the lymphatic system and you study immunity, this is the first line of defense. It is the border that anything that wants to do you harm has to cross. Things cannot do you any harm until it gets past this point. So it is the protective barrier. It has a lot of sensory receptors. We looked at two, the Meissner corpuscles, the Pacchian corpuscles. We briefly talked about the tactile ones, but I'm not worried about that. Those, the Meissner and Pacchian, because we looked at them in lab. That's what I want you to know. But sensation, you know, we've got all kinds of things sensing our environment through our skin. It does excrete some waste when you sweat. There are, like I said, some salts that are released. If you have to start using your skin to excrete waste, you're in trouble, right? You'll notice if you are in the healthcare field, you'll start seeing that like people that have kidney issues, they will start smelling like urine because their kidney isn't able to get rid of the waste products. It'll start coming out through the sweat, and that's a bad sign. It is an area of vitamin D production. Vitamin D is vital for a lot of things, but it's really important for, it's very important for calcium absorption. And so the sunlight's a really odd thing. I mean, it can be very dangerous, but it's also necessary. You know, living inside has its own issues. And also the regulation of body temperature. We looked at this in multiple portions. We talked about how it's, you know, the erector pili muscle. It's designed to try to create a little heat. And we talked about sweating and whatever, and we got a few more slides that kind of talk about that as well. But our body has a relatively constant temperature. 98.6, I think most people know 98.6 is what we consider normal body temperature. It is a set point that is monitored. You do need to know that the hypothalamus of the brain is what is setting our temperature. It's kind of like our built-in thermostat is in the hypothalamus. But the temperature of our body is kind of weird because it is controlled by the chemical reactions. Most chemical reactions release heat, but the temperature also controls the chemical reactions. One of the reasons why, if you are sick, and there's several reasons why you'll get a fever, but one of the main reasons is trying to speed up the metabolic reactions to help things fight off the infection. Now, heat loss through the skin, I'm the only one I'm worried about you understanding really is evaporation. Now we're going to go over this. These two are relatively similar. In physics, the main property is that heat always goes, or energy always goes from a hot body to a cold body. If I put an ice cube in hot liquid, it's not that the cool goes into the heat, it's the heat goes into the cool. Then it pulls the heat away from it. Energy always travels from hot to cold. And so this is a relatively cold board. If I put my hand on here, it's going to start pulling basically the heat out of my hand. That's called conduction. Now in the environment, I'm going to have, because this room is probably 74, I don't know, whatever. 74, 75 probably. Since I'm 98.6, I'm going to constantly radiating heat to the environment. Just like this board pulls out the heat from my hand, the air is going to pull out the heat from my body. Does that make sense? Again, not going to test you on these. These are more physics type things. Convection is simply if I increase the air flow, it's going to cause me to cool down. If you're in front of a fan, you can feel how much it cools you down, and it's just because the convection, as it goes past you, it pulls more heat. If you were going to thaw out something and you needed to have it done pretty quickly, one of the easiest ways and best ways is to have a little stream of cold water running on it. The cold water, as it's running through, it's going to keep pulling out heat. This is done by convection, pulling it out as it moves by. This is the one I want you to know a little bit about, evaporation, because this is how our body cools itself. These other ones we can kind of control on our own. You know, if you're outside, if you've been outside working in the yard or something and you're hot and you sit by a fan, you can go and, but this is something our body does instinctively. This is how the sweat works, right? So evaporation, anytime something changes phases, right? And in evaporation, we're going from a liquid to a gas. It requires energy. And so our body, if I am hot, is going to take all of my blood or a percentage of my blood and put it into that papillary region of the skin. It's going to vasodilate those blood vessels that are just underneath the epidermis. And then if I put some fluid on top of it, which we call sweat, when it evaporates, what it does is it pulls the heat out of the blood in order to change phases, and that cools us down. Right? So evaporation is how our body uses sweat. Makes sense. Now, this is again the same type of cycle we looked at it. There's another picture in this chapter of the big figure 8 as it's raising temperature, lowering temperature. So when our body temperature raises, our hypothalamus is going to sense it. Its job is to try to cool our body down. That means that, remember, homeostasis, negative feedback. If this is 98.6, all of a sudden I'm getting closer to 99 and up to 100. I'm outside and it's June and it's hot. Our body is going to vasodilate the blood vessels, like I said. It's going to cause vasoconstriction of the blood vessels, which means it's pushing everything it can up to the surface. And then sweat glands produce sweat and it evaporates. When we get cold, same area, the hypothalamus is going to do almost the opposite as far as the blood vessels go. It's going to vasoconstrict the blood vessels right under the epidermis to try and pull the blood away from the surface because, again, convection and radiation and all that are pulling the heat out. So I want to get away from that. Pulls the blood into my core to kind of protect it. And then it's going to start causing muscles to contract and relax. We call it shivering. Generally, if it's just slightly cold, it's just the erector pili muscles, but in general, those don't do it enough to get you warm, and so you start shivering. Right? So that's how our body regulates temperature using our skin. All right. Now, hyperthermia versus hypothermia. This is, I've become very hot. I have become very cold. Hyperthermia, too hot. Um, this can be very deadly here in particular in the southeast. Um, heat exhaustion, heat stroke, it can be awful. And what happens is here, because if it's too humid, evaporation requires the water to be able to put into something. And so if the air's already full, it can't evaporate. And so that's why it feels so hot here. Even when if it's 85 here and humid, it's very hot. If it's 98 in Arizona and there's no humidity, it doesn't feel hot at all. And it's because I can't evaporate that sweat. And so one of the weird things is here. I don't. Has anybody ever experienced like heat, borderline heat stroke, heat exhaustion? Good. But what you'll start feeling is the first couple of things is dizzy and nauseous. Pretty much right behind that, they'll start becoming a headache that's really not a fun headache. And then it's crazy because your skin will just dry up pretty quickly. It'll go from being sweaty to all of a sudden you're dry, and you'll get what, I hate to say it, clammy. It's just a weird type of a feel. Your pulse will start becoming what they kind of refer to as thready. It's real rapid and not really strong. It's kind of like your body's like, what's going on? I don't understand it. And this is dangerous. This can obviously cause death. If that ever happens to anyone in here, one of the first things you do, or know someone that does, you want to put a cold compress, hopefully ice, but you want to make sure you don't kill somebody with shocking them. But 3 areas. The main one is around the neck, because the first area and the only area you really need to protect is the brain. You want to put some kind of cold something around the neck to kind of try to cool the blood that's going to the brain. The other 2 areas are the axillary and groin area, because those are the areas where large arteries are very superficial, and so you can affect cooling the blood at those areas. So just a little FYI. Hypothermia, you get too cold, It can happen here, but if I went up to, I was supposed to go a couple years ago to a Chicago Bears football game in December, the December before Christmas. It was a night game, and I decided not to because I'm a Southern boy now, and I was a little bit scared of how cold it would be because I would suffer this. But this is odd in the fact that it starts lowering your body activities. If you've ever been really cold, you'll find like sometimes you can't move your hands, and it's hard to move things, and it's like you start slowing down, loss of reflex, and then you'll lose consciousness. It actually puts you to sleep in a weird sort of way. Not that that's a good thing. But hyperthermia is high blood pressure. Hypothermia is low blood pressure. That's the main thing I want you to know. Inflammation. I always love this one. So what color is blood? Red, right? So if I put blood in an area, it's going to be red. If I'm putting blood in an area that doesn't have blood, that is abnormally amount of blood putting in, it's going to swell. Blood is warmer than the tissues around it. Its job is to carry heat around, so it's going to be warm. And if it's going to a place that's already hurt, it's going to be painful. I mean, I want to put a red hot liquid in something that's injured. It's going to be red, swollen, warm, and painful. Hopefully you don't have to study that. That's kind of something that you should just go, okay, that makes sense. Right? Swelling, this is not to be confused with something like edema. Edema is a different ballgame. This is normal. This is our body's response to an injury that we're trying to first wall off, but also bring white blood cells into there to try and help fight whatever's been damaged. So swelling is, again, one of the things that our integumentary system, the cutaneous membrane and skin, will do to try and stop spread of an infection or respond to an injury. Now, this book, it's very strange. There is more than just shallow and deep cuts. I mean, there's other categories kind of in this. But this is what we have. All right. Shallow cuts simply are cuts that do not get through the epidermis. This would be like what we consider a scratch, basically. A deep cut's going to get into the dermis and sometimes down to the subcutaneous layer. Now, if it does this, hopefully no one in here has seen this, but you might have. If you see a cut that's so deep you start seeing the yellow, the adipose tissue, you are into the subcutaneous layer and sometimes even below it. Now, in 211, when you get into the blood system, you're going to talk about the clotting mechanism. In here, all I want you to know is clots form from deep cuts. They turn into what we call scabs. Right? That's all you need to know in this portion right now. Now, fibroblasts, which were cells that we looked at before, these fibroblasts come in, and their job is to lay down the fibers. Now, if the fibroblast comes in and lays down all collagen, you're going to end up having what we call a scar, a keloid. Right? Scars have no elastic fiber in it. That's why a scar doesn't stretch, it doesn't pull, it has no elastic fiber in it. If these fibroblasts, some people just are predisposed that when they heal, their fibroblasts produce mainly collagen and not elastic. Some people scar easier than others. If the injury is big, then all those cells are worried about is repairing it, and they just put collagen fibers in. That's why the worse the cut, the more a chance of having a scar is, right? What do you think growth factors do? Cause things to grow, right? Don't overthink it. So I've got a cut. I'm going to release hormones that are called growth factors that are going to get the cells that are along the side of it to start growing to repair it. I'm going to bring in phagocytic cells, some of them are dendritic cells, some of them are just macrophages, whatever. They're going to come in, they remove the damage, they get rid of the bacteria, anything that's made its way through the breach that we call this deep cut. and then move on. And so deep cuts basically, again, they go through the epidermis, they get into the dermis at least, sometimes into the subcutaneous layer. At this point, because they've damaged the capillary, we're going to have a blood clot, which turns into a scab. Underneath it, we're going to have fibroblasts that are repairing the fibers. We're going to have macrophages or phagocytic cells coming in, getting rid of the debris, and we're going to release growth factors that are going to cause the things to grow. Makes sense? All right. I really wish this was on one slide. Burns. I want you to know more than just first, second, and third degree burns. And I hope everybody understands first degree burns are the least severe, second the next, and third degree burns are the most severe, right? If I gave you the scientific name for them, I would hope that you would be able to, just through common sense, figure out the order, right? So these two are partial thickness. So if I'm telling you I've got partial thickness on one hand and full thickness on the other, which one do you think is the bigger, deeper burn? Full thickness or partial thickness? Full thickness, right? Full thickness is the third degree burn. It means it burns the entire cutaneous membrane. Full thickness. If it is partial thickness, we know that it's not third degree then, and then it's either superficial or deep. Which one do you think is superficial? The superficial one. The deep one is deep, right? So just through a little bit of common sense, you should be able to put these in order. Superficial partial thickness is a first degree burn because it is superficial and not on the whole thing. Partial thickness. Deep partial thickness is still saying it doesn't go all the way to the bottom, but it goes a little deeper than superficial. This is second degree burns. Full thickness is third degree burns. Now, superficial partial thickness, these first degree burns, they again do not get past the epidermis. Now, it says as in sunburns. Now, I don't know about you, but I've had plenty of sunburns, unfortunately, that were not first degree burns. This is talking about the sunburn of, oh, I was outside for like 10 or 15 minutes and my arm turned red and it was a little bit warm and it kind of stung a little bit. This is not talking about the type that blister and, you know, cause real issues. Right? This is just the top layer. So this, again, is not going to blister. It'll heal in a few days. It says to weeks, but it really will only take a few days for this to kind of go away. This is the type of sunburn that generally is not going to necessarily peel. It might peel a little bit, but it's not, again, blistering. Deep partial thickness. The reason that this is called partial thickness is this gets into the upper part of the dermis. This gets into that papillary region of the dermis. And once we burn that part, now we're talking about that capillary bed. So now I've damaged the capillary bed in the upper part of the dermis. This will have blisters associated with it because now I'm releasing fluid. I've got an issue. It is going to, again, it's still, this is not a great, I'm not saying, ooh, go out and get this. But this is still not usually going to cause a scar. It's going to heal pretty readily. It will move on. Right? Again, this is a bad sunburn as far as what most people would be associated with that. Now, third degree burns. Third degree burns are called full thickness burns because they get deep into the dermis. They are going to basically burn the entire cutaneous membrane. These very rarely, if ever, will heal on their own. They will have to have skin grafts. They will always have scarring, depending on the size of it as far as heal on their own. This is a major injury. If it is over any relatively large part of your body, it will require very special treatment because now your first line of defense is gone and you are at the will of anything that wants to get into you. If it's over a fairly decent part of your body, you will have to live in a sanitary environment until it is healed. Anybody here ever have a third degree burn? All right, good. It's odd, and I'm not going to test you on this, but it actually at the time, most people that have had third degree burns will say they don't feel the pain, and it's because it will burn all of the nerve fibers at the time. Now it becomes very painful later, but at the time it is so bad that it basically shuts down your system of sensory, and so it, they'll have a lot of time. I've been around someone that had it, and they were like, "I'm fine." I go, "No, you're not." Um, Now, when we talk about burns, we divide the body up into regions, and we call this the rule of nines because it's 9%. Right? And so this is how we, can estimate the recovery and what we need. And so, for instance, the arm, from the shoulder to the fingers, front and back, the arm is considered 9% of the body. So if I have a burn on my right arm from my fingertips to my shoulder, it's a 9% burn. If I have one from my fingertips to my elbow, because that's basically half of my arm, that would be a 4.5% burn. If I have a burn on the entire anterior surface, fingers to shoulders, but only on the anterior, again, 4%. Right? Makes sense. The leg is twice as big as the arm, so it's considered 18% in total, and the same rules apply. Toes to hip, 18%. If it is just toes to the knee, that is 9%. If it is toes to the hip in the posterior and only that, then it's 9%. I'm not going to ask you some kind of crazy percentage. It would probably either be in total or half. I'm not going to go, oh, I burned a finger on one hand and an elbow on the other arm and whatever. It'll be, all right, I reached into a fryer, or something like that. Make sense? So far, so good. The head, total, 9%. Front 4.5, back 4.5, whatever. The trunk, the actual body, 18% front and back. So if I just burn if I'm doing something and I just burn my back, basically an 18% burn. The only one that doesn't apply to that is this area, and I will never ask you about a burn there. That just, no, right? So that might not be 9%, but no. And then the worst slide of all, lifespan changes. I will never ask you anything about this because getting older sucks. And none of these will ever have anything that say, oh, it improves. It just is how it breaks down. And so that is that. All right, so chapters 5 and 6 are going to be on our test. All right. I think y'all did a pretty good job of doing the connect. So the test is going to be Monday. Do the connect. I mean, again, it's free points, but it also helps you study. I wish that I had things that I could, I'm